Welcome back to the workshop for another example on determining convergence and divergence of series. In this example, what we actually want to do is we just want to decide which test to use in determining convergence or divergence. So we don't actually want to decide if any of these series converge or not. Rather, we just want to say, well, what method or what test should we use? So as we build up our methods and our ability to observe, we will continue to look at these examples where we have to make these decisions. So right now, all we have is the nth term test. We can observe a series as a geometric series. We have the integral test, and we can observe a series as a p-series. So those are the four classifications or the four approaches or the four tests that we can choose from for this example. So for the first example, we have the sum from 1 to infinity of 17 over n to the negative second power. All right, so you might say to yourself, oh man, that looks really nice. That looks exactly like a p-series. That's fantastic. So you might say p-series. And while that's a perfectly appropriate thing to think, in this case, it's actually not a p-series. What we have is we have an exponent on n. Well, we could think of that as p. For the p-series, we're specifically looking at p-values greater than 0. So this doesn't actually fit the definition of a p-series. We would need this exponent to be greater than 0. So it's not a p-series in this case. We do have a couple of options, though. We might suspect that the terms go to 0, or that maybe they go off to infinity. And what we would want to use here is the nth term test. That's always a really good place to start because it should be pretty simple for the most part. If it goes to 0, it's inconclusive, which is not helpful. But what is helpful in this case is first observing this series as the sum from n equals 1 to infinity of 17 times n to the second power. Notice that with this negative exponent in the denominator, we can rewrite it in the numerator with a positive exponent. The nth term test will tell us what we're looking for in this case, or if we were determining convergence or divergence. So this is what we want to take a look at. All right, let's see here. Next, the sum from 1 to infinity of 17 times n to the negative second power. Well, this is actually pretty similar to the last example. You could say to yourself, what should we do here? Well, if you had decided to not rewrite this, you might say to yourself, I'd like to try the integral test. And that's perfectly acceptable. We have some things that we would have to check, namely that the function of interest is continuous, that the function of interest is positive, and that the function of interest is decreasing. It would satisfy all of those, and we could use the integral test here. But again, this is just a list of things that we could try, or that would make sense to try. So integral test would make sense to try. But if we first observe that this can be rewritten, much like the last problem, n equals 1 to infinity of 17 over n squared, now we do have something that is looking like a p-series. So we can actually observe this as a p-series. So, or p-series. So we have a couple of options for that one. It actually works out that as far as p-series go, the fact that they converge or diverge can be proven using the integral test. So these are essentially just a particular case that work out really nicely. When you have it, it's simple. Otherwise, it's really just a scenario where you could use the integral test. All right, for the next example, we have the sum from 1 to infinity of 17 divided by negative 2 to the n. So this looks a little bit different again, and so you have to ponder, oh man, well, what does that really look like? Well, maybe rewriting it also would be helpful. So you could say that this is the sum from n equals 1 to infinity of 17 times 1 over negative 2 to the nth power. And suddenly it becomes hopefully quite obvious as to what we can use here. We can use the observation that this is, in fact, just a geometric series. For some geometric series, we could actually use the integral test as well if we failed to observe that it was a geometric series. In this case, because it's alternating between positive and negative values, an actual function, letting this be x, having a base, an exponential function with a negative base, does not make sense. That's a no-go. So this is a geometric series. If this were positive, a positive value for r, then we could have used the integral test. All right. So geometric series. For the last example, we're taking a look at the sum from 1 to infinity of 2 plus the sine of n over n. So what's really nice here is we say to ourselves, this is clearly not a geometric series. This is clearly not a p-series. And let's see here, the nth term test, we could quickly see that 2 plus sine of n is bounded. It lies within a couple of different values. So the nth term test would not do us any good. So we say to ourselves, well, Dr. Reinhout, that must mean we need to use the integral test. Integral test. And that's a great thing to think. That's exactly what you should be thinking right now. However, if we were to say to ourselves, consider the function f of x equal to 2 plus the sine of x divided by x, we would find that its derivative would be x times the cosine of x minus the quantity 2 plus sine of x all divided by x. And because we have x times the cosine of x, as we continue on along the real line, looking at x values that are getting large, we'll find that this goes positive and negative, right? So overall, this is going to go positive and negative. Because this x times cosine x will overtake 2 plus sine x. Of course, they'll get small because x is becoming small as well. But even just this guy right here, this gives you just cosine of x. And then this would give you something really small. Anyway, the point is you'll end up with positive and negative values in the derivative as you continue on, and telling us that this is not a strictly decreasing function, so the integral test cannot be applied. Well, what that really means for us is that we don't have any methods right now to determine if this converges or diverges. Well, so what do? Well, we develop more methods. So we'll continue on. We'll find additional methods. I don't remember the exact count right now, but we'll end up with something like between 6 and 8 different methods for determining if a series converges or diverges, because it's not necessarily an easy question to answer. Furthermore, notice that in these additional methods, the integral test in the p-series, much like the nth term test, we were unable to actually find the sum of the series. And that is the case for most tests. We don't have the ability to find the sum, but we do have the ability to determine if that sum is finite, if the series converges. All right. I look forward to seeing you guys again soon back here in the workshop. I hope you have yourselves a wonderful day.